Superconductors, an unknown material among the general public, but among scientists and chemistry students, yes, those are chemistry students, they're what I like to call revolutionary. Let's start with Vladimir Lenin. Just kidding, that's H. Kamerlingh Onassis. H. Kamerlingh Onassis discovered superconductivity in 1911, who was undergoing liquefaction investigations when he found a way to liquefy helium gas. If you didn't know, liquefaction is the process of turning a gas into a liquid. It was just made possible to liquefy a gas like helium, which produced extremely low temperatures at the time. If you compare the temperature of liquid helium to the boiling and freezing points of water, there's an extremely huge gap. Now, absolute zero's temperature is at about negative 273.15 degrees Celsius. Liquid helium, negative 270. They come pretty freaking close to each other. They're both cold and, lacking warmth. So yes, superconductors are cold as hell, lacking warmth. In Onassis times, superconductors were metals like mercury, lead, and bismuth, but only if they came to the extremely low temperatures that liquid helium has. Over that time, various alloys were found that were superconductors at somewhat higher temperatures. Unfortunately, none of these alloy superconductors worked at temperatures much more than 23 degrees Kelvin, which is at least negative 250.13 degrees Celsius. Now, the only chemical properties in superconductors are the elements: water, earth, fire. Wait, who the hell wrote this? Aristotle, get out of my room! Anyway, the only real chemical properties of superconductors are from elements. Chemicals, alloys, ceramics, superconducting peptides, or organic superconductors. Other than that, superconductors show resistivity. Metallic mercury, for example, decreased suddenly to zero, rather than continuing to decrease slowly with decreasing temperatures as expected. Onassis called this phenomenon superconductivity, because a resistivity of zero means that an electrical current can flow forever, like shown in this picture. As for the physical properties of superconductors, this is where I really think that superconductors shine through. However, they're different from regular conductors because they're super, of course. What superconductors do that regular conductors can't is that superconductors, when conducting electricity, use no energy. They're special metals that follow a certain rule called the Meissner effect. Now, a superconductor is what's called diamagnetic. TLDR, a superconductor can levitate in a magnetic field, like this. No heat would be generated while the current moves through the conductor because, as mentioned before, they use no energy. Not a pint. No energy. Nada. Superconductors can carry currents much more compact than copper can. This means that they come in much smaller quantities as opposed to wires that connect to your computer. From MRI scanners to choo-choo trains, these small, low-temperature materials can actually do a lot of things you wouldn't expect. Magnetic resonance imagers, also known as MRIs, in the hospital rely on steady and reliable magnetic fields. Because duh! How else are MRIs going to function? MRIs use powerful magnets, which produce a strong magnetic field that forces protons in the body to align with that field. Everybody knows that, right, Aristotle? Most MRIs use superconducting materials. And what is the superconducting material they use? Niobium titanium, an alloy that becomes a superconductor below 9.4 degrees Kelvin or negative 263.75 degrees Celsius. The scan coming from an MRI uses a strong magnetic field and radio waves to generate images of body parts that can't be seen as well with X-rays, CT scans, or ultrasound. Aside from MRIs, here are a list of things that use superconductors that I'm too lazy to talk about.
Shielding of magnetic fields, superconducting electronics and quantum computers, superconducting magnetic energy storage, superconductors to use and quickly accelerate charged particles, power transmission cables, transformers, motors and generators, fault current limiters, magnetic levitation including magnetic suspension, contactless, bearings, linear motors, and trains. The question in some people's minds right now are how can superconductors actually save power efficiently? One of the few things I mentioned that superconductors could actually be applied to are superconducting magnetic energy storages, or SMES. This is a system that traps electricity within it by forcing it to flow inside the SMES until it needs to be used again. Since superconductors are involved, that means there's no actual energy being used. As of now, we can't store electricity for long periods of time, but
But with superconductors, we can essentially store them for as long as we want.
Innovative.
Taking that into account, if we could hypothetically use those wires to supply power in a city, that could save not just energy, but money. Generating and carrying electrical currents with very low energy losses, production of large magnetic fields, new transport systems, design of new electronic devices, there are many things superconductors can be applied to. The only real limits of using superconductors are that it's going to be difficult to maintain the low temperatures that they have, and not to mention expensive to start off with. They're also very brittle, which means yes, they're tough, but are also very fragile. And I'd say the biggest concern is that they're chemically unstable in some environments. Superconductors started off as a small experiment, but now they're one of those things that can really help the world in the near future. Scientists are still trying to research ways superconductors can be applied to people's everyday lives. There are some drawbacks, and superconductors can be dangerous if present in certain environments. If we can find a way to maintain those low temperatures required for superconductors to function, and find a way they can be used in every environment, we'd be saving so much energy. Now that's what I like to call revolutionary.